Hello, everybody. Welcome and thank you for joining us. I'm Roberto Martinez with the WolframU team. We are ready to start this simulating EV dynamics with system modeler webinar. Today's presenter is Enkit Naid, and Leonardo Laguna will be our Q&A support. So please use that pane to post your questions and comments. Thank you very much for answering that poll question. We couldn't ask for a better mix of in our audience. I'm sharing the results with you right now. Um, we would also like to know what's your experience using um, System Modeler. Please let us know by answering the poll that I'm sharing with you right now. Give me 1 second. There's the poll. Take some time to check it out. In the meanwhile, let me remind you that you can download today's notebooks by clicking the green link that is in the right part of your screen. This is important because this will help you improve your understanding of today's event. And also remember to use the Q&A pane and note that this session is being recorded and will be sent to your email later today. We are also live streaming to our 3Wolfram YouTube channels. To the folks there, if you have any questions, please use the chat and we'll answer you back as soon as possible. Or if you'd like to join the live session, there's a link in that pane. Thanks again for answering that last poll. Let me share the results with you. For those of you who are new, or even if you don't have an Aptic license at the moment, we have a free 30-day trial. In case you want to download the system modeler, let me share with you. There's the link. Check it out, and thank you for letting us know about your experience with System Modeler. So without further delay, I will pass things over to Ankit. Please enjoy the session.
Hi everyone, I'm Ankit, an applications engineer at Wolfram the team behind System Modeler. In this session, I will walk you through my exploration of simulating electric vehicle dynamics using System Modeler and how we can answer practical questions using physics-based models. This journey started back in January when my brother casually asked, "Can I drive from Brooklyn to Boston on a snowy day, that too with a headwind?" At first, the answer seemed straightforward. A quick web search gave me an expected range estimate, but it left me with more questions than answers. Why is the range 400 kilometers and not 300? What technical factors affect this range? Why does it drop in cold weather or on hilly roads? And more importantly, how can we quantify all of this? That curiosity led me deeper, and I realized EVs aren't just cars. They include electric bikes, drones, even lawnmowers. Understanding the dynamics is key to designing and predicting behavior across this whole category of electrical machines. In this webinar, we will explore three key questions. First, how far can you drive with a given battery and motor configuration? Second, does driving in the city versus on the highway make a difference, and why? And third, how do external factors like temperature and terrain affect the drive? By the end, we will not only look at the what but also the why backed by simulations. Before we dive into the model, let's take a step back and ask, why simulate at all? There are 5 key reasons that stand out. First, simulation helps with early stage component sizing. You can estimate motor torque, battery capacity, and output profiles. So you know how to size filters, inverters, or cooling systems before you build anything. Second, you can test how the system responds to unforeseen events like extreme cold weather, overcurrent, or electrical faults. It helps you to verify behaviors in a virtual environment. Third, hardware testing is expensive. Between equipment, setup, and energy costs, it adds up fast. Simulation reduces the number of real-world tests you need. Fourth, for AI or ML training, you often need large data sets, and simulation can generate synthetic data quickly than collecting it on the road. And finally, simulation gives access to internal variables that sensors can't capture, like internal resistance losses, heat generation, or magnetic flux. This helps diagnose or optimize designs in ways physical testing can't. With that in mind, let's jump into our EV model and look at the simulation results. Let's open up the model in System Modeler. For those of you who are new to it, this is the System Modeler's modeling interface. You can build models visually using drag and drop from the built-in Modelica library. This library includes hundreds of components from domains like electrical, mechanical, and thermal systems. Throughout this presentation, we will look at several of these components more closely and see how they connect to simulate electric vehicle behavior. Here you can see the top level EV model. The EV is connected to a velocity profile representing how the vehicle moves, and to an ambient component with a temperature input. These components are hierarchically structured, meaning each block contains subcomponents, which you can explore by double-clicking. Let's zoom in one of the EV block. Inside, we see a detailed view of the EV architecture: motor, gearbox, controller, inverter, battery, and thermal systems. You can continue drilling down into any component and even switch to text view to inspect or modify the underlying equations. For example, in a resistor block, you will see Ohm's law implemented explicitly with voltage and current relationships. You are not limited to built-in components either. You can define your own custom models from first principles or experimental data. Let's return to the top level and now explore each of the major components one by one. Let's now walk through the major components of the EV model. We start with a battery, which acts as the energy source. In our case, it provides a DC voltage of around 350 volts. That DC voltage needs to be converted into AC before it can power the AC motor. This is done by the inverter, which sits between the battery and the motor. The motor produces torque, but at a very high rotational speed, often around 20,000 rpm. To match the wheel speed, this needs to be reduced, typically down to about 2000 rpm, and this is done using a fixed gear reduction stage. From there, power flows into the car body model. This component accounts for all the external forces acting on the vehicle, including aerodynamic drag, rolling resistance, gradient forces. There is also a control unit which monitors vehicle speed and regulates current supplied to the motor to achieve the desired driving profile. Finally, we include thermal components, one for the battery and one for the car, to simulate how heat builds up or is dissipated during operation. Of course, in a full vehicle model, there are many other components such as DC-DC converters, auxiliary batteries, and accessory systems. But for this presentation, we will focus on the core powertrain and thermal systems. Let's take a closer look at the battery component, which plays a central role in EV performance. There are different types of battery chemistries used today, such as LFP, NMC, and LTO. Each chemistry has its own characteristics, and one of the most important is the open circuit voltage versus state of charge or SOC curve. In the chart shown here, you can see how the voltage changes as the battery discharges. NMC cells deliver the highest voltage, around 4 volt at full charge. LTO cells deliver lower voltage, around 2.5 volt. LFP, though not in the highest in voltage, has a nearly flat OCV curve, which means the open circuit voltage stays stable across a wide SOC range. This ability is one reason why LFP has become widely adopted in many EV platforms. Now, this data is for a single cell. In a real battery pack, however, cells are arranged in series and parallel to reach the desired voltage and current capacities. Let's get back to system modeler. In our battery model, we can define these parameters: number of cells in series to get the total voltage, and number of cells in parallel to get the total current capability. For the cells, we can also provide the internal resistance, nominal charge, and define the OCB curve itself. The model also includes the electrical dynamics of the cell. Internally, each cell is modeled with a primary series resistance and one or more RC circuits to represent the transient behaviors like hysteresis. There is also a heat port built into the battery model. This port gathers all the thermal losses caused by the internal resistances. The heat is passed on to a thermal capacitor, which is a lumped model representing thermal mass. Its capacity is calculated using the formula mass times specific heat capacity. This thermal capacitor can be connected to a cooling or heating circuit, for example a refrigerant loop, to simulate active thermal management. Lastly, a note on connections in System Modeler. You will see red and blue lines connecting components. These aren't just input and output signal wires. They represent energy carrying domains like electrical and thermal connections. So this approach ensures that the conservation laws like energy and mass balance are automatically enforced and that connections stay consistent within the physical domains. You cannot directly connect an electrical wire to a thermal capacitor. Let's now simulate a simple battery test scenario. In this model, we draw a constant current of 100 amperes from the battery pack, which is a typical discharge profile for a sustained load. As expected, you can see the voltage output starting at around 370 volts and gradually decreasing over time. This follows the OCV versus SOC curve we discussed earlier. As the state of charge drops, so does the voltage. Now, let's take a look at the battery temperature. Here we see something critical. The temperature rises rapidly and reaches nearly 500 degrees Celsius in just 30 minutes. This clearly illustrates the effect of internal resistance losses, even at moderate discharge rates. Of course, in real system, thermal management would prevent this. But this test shows why modeling thermal behavior is essential and why cooling systems are not optional in high power applications like EVs. Without proper heat extraction, the battery can quickly enter unsafe operating conditions, affecting not just efficiency but also safety and lifespan. Electric vehicles can use a variety of motor types, but the most commonly used in modern designs is a three-phase AC permanent magnet synchronous motor or PMSM. These motors are popular due to their high efficiency, power density, and good performance over a wide speed range. In our model, I have used the three-phase permanent magnet synchronous machine component from the Modelica library. This component is based on physical equations and allows you to specify key parameters such as stator resistances and inductances, permanent magnet flux linkages, torque constants, and mechanical losses. One useful feature of this model is that it is bidirectional. It can operate both as a motor and a generator depending on the power flow direction. That is essential for simulating regenerative braking scenarios, where the motor recovers energy and sends it back to the battery. On the mechanical side, the motor is connected to a shaft model which includes a rotational inertia to simulate the mass of the rotating components, a damping element to represent friction at the shaft or bearing level. Now let's simulate a simple driving scenario. The vehicle accelerates from 20 to 100 km per hour. As expected, the motor power and torque increase during acceleration. Once the target speed is reached and the vehicle cruises, the required power and torque drop and stabilize. This reflects typical EV behavior, where high torque is required at low speeds for acceleration and lower power is needed once cruising. Now let's take a look at the car body component, which brings together the mechanical forces acting on the vehicle. This component accounts for four main forces: traction force, that is generated at the wheels by the motor via the drivetrain; gravitational force, due to the weight of the vehicle when it moves along a slope or gradient; rolling resistance, caused by the deformation caused by the friction between the tires and the road surface; aerodynamic drag, the resistance from air which increases with speed. In our test simulation, the vehicle moves over a constant incline while accelerating from 0 to 100 km per hour. Let's simulate and see the results. The rolling resistance and gradient force remain constant since they depend on vehicle weight and slope. However, aerodynamic drag increases quadratically with velocity, meaning it becomes a dominant factor at higher speeds. To move the vehicle, the traction force generated by the motor must overcome all of these resistance forces. In addition, it must supply extra force for acceleration, especially in the early phase of motion. This component gives us insight into how external forces interact with the drivetrain and how energy demand changes as the vehicle moves. So far, we have seen how I modeled the key components of the electric vehicle, from the battery and motor to the car body. One of the strengths of this approach is flexibility. Depending on your modeling objective, you can increase or reduce the level of fidelity. For example, you can use a detailed electrochemical battery model or simpler data-driven interpolation curves. For our test case, the current level of fidelity gives us the right balance between accuracy and simulation speed. Now let's return to the original question. How far can this vehicle drive on a single charge, and how do external conditions affect that range? To keep things simple, we will assume the car drives at a constant speed of 110 km per hour on a flat road. Under standard conditions, the vehicle travels about 400 km on a full charge. If there is a headwind of 20 km per hour, the range drops to around 360 km. But if the outside temperature falls to minus 10 degrees centigrade, the range drops further to just 300 kilometers. That's a 25% reduction in range from 400 to 300 km caused by cold weather. This drop is primarily due to increased energy usage for cabin heating. We will look at this thermal effect more closely in a later slide. The next question we asked was, how does city driving compare to highway driving in terms of range? In city driving, we typically deal with traffic, lower speed limits, and frequent stop and go movement. This results in regular acceleration and braking. For this simulation, we used a driving cycle where the vehicle speed fluctuates between 30 and 70 km per hour, mimicking typical urban traffic. We run the simulation until the battery reaches a minimum SOC threshold of 20% to simulate practical usage. Surprisingly, the vehicle travels up to 500 km in this city scenario, significantly more than the 400 km under highway conditions. So, what contributes to this increased range? First, aerodynamic drag is much lower at city speeds. It drops from around 800 newtons on the highway to about 400 newtons in city driving. Since drag increases with the square of speed, this has a major impact on energy consumption. Second, the motor acts as a generator during braking, recovering energy. In our simulation, it generates peaks of around 8 kilowatts during regenerative braking events. And third, battery cooling demand is lower in city driving. At high speeds, the battery generates more heat and needs active cooling. At lower speeds, thermal losses are reduced, meaning less energy is spent on keeping the battery within safe operating temperature. Together, these effects combine to make city driving more energy efficient, even though it may seem counterintuitive. Now, let's look at the impact of terrain on energy consumption and range. Let's say you're driving uphill on a road with a constant slope of 7 degrees, a typical mountain ascent. In our simulation, after driving for 2 hours, the vehicle ends up with around 40% state of charge, compared to about 60% state of charge if it were driving the same speed on flat terrain. That 20% difference highlights the additional energy required to overcome gravitational resistance when climbing. However, there is an important consideration here, something that's easy to miss in range estimates. If you're driving back downhill, the situation reverses. The motor can act as a generator, recovering some of the energy that was spent climbing. This is an example of regenerative braking, where potential energy from elevation is converted back into electrical energy and sent to the battery, rather than being lost as heat. So, while uphill driving reduces range, terrain isn't always a one way loss. In looped routes or round trips, net elevation change matters more than the presence of hills alone. Let's return to the topic of temperature, because where you live can make a significant difference in vehicle performance. This uncertainty plot shows how range varies with ambient temperature. If you live in a region where winter temperature drops to about minus 10 degrees centigrade and summer temperatures reach plus 30 degrees centigrade, you can expect the driving range to vary from around 400 kilometers down to around 300 kilometers, a 25% reduction. The main contributor to this drop isn't just battery chemistry, it's space heating. In cold weather, energy is diverted from the battery to heat the cabin. In our model, we use an electric resistance heater which turns on when the cabin temperature drops below a set comfort level. This adds a continuous energy load during winter driving. So, it's just not cold batteries, it's also the need to keep passengers warm that reduces range in cold climates. In modern EVs, space heating is often handled more efficiently using heat pumps instead of simple resistive heaters. Heat pumps work by transferring heat from other parts of the system, including the drivetrain or ambient air, and can be significantly more energy efficient. One interesting opportunity, especially in colder climates, is to reuse the heat generated by the battery itself. In System Modeler, this is easy to explore. You can tap into the battery's heat port and redirect that thermal energy to the cabin space using a thermal connection. Or you can go a step further and model a full fluid coupled heat pump circuit. I will leave that as an open exercise. Try building this in System Modeler and see how much range you could save by reusing the waste heat. And finally, to summarize, simulate before you build. It helps identify design issues early before committing to hardware. Terrain, temperature, and traffic conditions all have a significant impact on range and performance. And finally, virtual models let us measure what's otherwise unmeasurable, from internal thermal losses to hidden energy flows. With that, thank you for listening to this presentation, and now let's open up for Q&A. Yes, hi Leo. Uh,
Hello.
so yes, so Rob's like while preparing for Q&A, I think we have prepared some polls. So let's start the polls and see and check how much people have been attentive towards the presentation. In the meanwhile, Leo, if uh, have you prepared some questions for me to go over based on the your review of the presentation?
Yeah, I was thinking a few. So I was curious about the gear component of of the EV. So
Right.
how does it look like? I I don't I'm more I have more experience with the electrical part, but not with the mechanical. So
Yeah. Yeah, you are the electrical guy, but yeah, in the gear model, in my case, it is a very simple model. It's a fixed, it's an ideal gear, so I'm not considering the gear losses. So it's basically you just use the fixed ideal gear component from the rotational library in the Modelica package, and then you can just define the gear ratio. In our use case, the gear ratio is 9, which is a typical gear ratio in EVs. And then to model the rotational inertia, I have a shaft component as well.
so this component could be changed for some kind of automatic shifting gear, right?
Yes, yes, yes. Yeah, basically, what we have here is we have ratio defined as a parameter, and if you want to change things while simulating, you might want to change it as a real input and then play with the input if you want to change it on the fly.
All right, that would be like a way of making a simplified modeling, uh, a simplified model of a gearbox. But
Yes,
I have seen also some Modelica models or system model models. Probably you don't have them here, where they try to model like a full automatic gearbox. So I
right,
guess it should be possible to plug it uh,
right.
if you wanted to have like a more complex model of the gears. But I guess that in this case
For
is good enough.
For EVs, you don't need that complex gears because the torque the motor provides is almost constant, and it's highly efficient for a wide speed range. So you don't need to vary the gears that much. But yeah, of course, if
Right.
you can have a complete logic behind this, and then you can model that. Okay, Leo. In the meanwhile, if you can show the results for the first poll. So yeah, which is not a key component of an electric vehicle exhaust system, right? Um, Inverters, of course, is a key component of the EVs. Uh, okay, so Rob says a second poll, please. Right. In which driving conditions do EVs generally deliver better range? Yes, it's city driving, and the reason is primarily because of the regenerative braking. Um, so, yeah, first one is the right answer. And then, Robs, if you can show the third poll. Yes, which type of motor is most commonly used in modern electric vehicles? Uh, It is permanent magnet synchronous motor, but in I think when it started, it was induction motor, and currently it's primarily permanent magnet synchronous motor that's being used. Yes. Okay, Leo. Do you have any other questions for me?
Yes. So well, in this case, more than a question, it was just like a comment. I don't know if you're aware that there are like communities of people DIY that are creating their own electric cars. So you don't need to buy them from any company. They what they do is they create or manufacture their own battery packs, replace the motor with batteries and the electrical parts. So this kind of modeling is will be very useful for for that community because it allows them to calculate how much battery do they need to carry.
Yes. And one very much related field is that we have helped some of our customers is in drone modeling as well, because in drones there the voltage profile from the battery is also very important. Like if the voltage changes, then the force generated by the propeller that changes as well. And it's also very much similar Of course, it does not have this AC motor in it. It has this brushless DC motor, but there as well, the concept is similar.
Yeah, and I was thinking, I don't know if you had it in this model, but it's surely possible or very easy to do. For example, if you want to add more cells to your battery, how much weight is going to add to your car,
Uh,
and also you should be able of calculating the range for.
yes, um, right. So, yeah, in the battery model, one thing that we do not have by default is the weight of the battery. So the way I have defined it is, if I go into the car body, we have this vehicle component, and there we have the dead weight of the car, which I think we takes account into account the battery weight as well. But yeah, if you want to test, okay, if I have 5 passengers, if I want to have more luggage, then you can manipulate this mass parameter, and then you can check uh, how it would affect.
Right. So now that you mentioned the battery model, so it was you also consider the thermal management, right?
Oh yeah, yeah, oh yeah, yeah. That is something I did not cover. So in the battery model, of course, in a real EV, you have a very complicated circuit. But in my case, just to represent uh, the scenario, let me just show. Yeah. So I take the heat input, I convert it into a real signal, because the heat port that I have, I cannot directly use it with my controller circuit. And here I have a simple PID controller which tries to set the battery temperature at to 25 degrees centigrade. And from there, what I do is I have a very minimal cooling circuit, basically a fluid at a constant temperature going from left to right. And what this PID does is it manipulates it changes the mass flow rate of the fluid passing through the pump, so that it can absorb all the heat. uh, right. But in a more complicated, in the real in a real circuit, you will have more detailed coolant circuit with pumps, valves, and a different configuration. But for this scenario, I just showed that it's possible to combine the control logic to a coolant circuit. So
Right. So
you
this is
about the
this is more like the radiator of the gasoline cars that you have a place where it is where the liquid is being cooled, right? And then it flows into the battery. There is like a change of heat, right?
yes, uh, yes, uh, yes. Let's take some questions, Leo. Uh, so one question was, are the exam? Okay, one question was, how do we get access to the models that I showed here? Uh, so if you have, yes, if you have the same version of System Modeler and Mathematica, and if you have version 14 point, was it 3? Yeah, 14.3, then it should work automatically. So if you have Mathematica 14.3 and if you run the initialization command, the model should automatically load in System Modeler 14.3. You don't need to do anything. But if you have a different version of System Modeler and Mathematica, you would need the model. And Robs, after this, maybe I can send you the model after this webinar, and you can send it via mail to all the participants later on.
Yes,
So
thank you.
yeah, uh, yes, um, right. So the next question is from John. Can I give quick brief overview of the key vehicle parameters? Uh, right. So in my car body, the vehicle component that I have used, if I open the documentation for it, I would right click and open the documentation. Here you could see how the vehicle model is modeled, like how the different resistances are calculated. And here you could see the different parameters that you can set. You can set the total mass of the vehicle, the wheel radius, the frontal cross sectional area to compute the air drag, um, and the rolling resistance coefficient and other things. In our example, we had a constant inclination, but you also have the flexibility to add uh, a variable inclination, like as you would have uh, in a real drive. The inclination would change as you move, and you can feed the data to this model, and it will compute the traction hypothesis accordingly. So yeah, you can define the variable wind speed as you move along, as well as the inclination as real inputs to this vehicle model. Yes. Right, Leo. Are there any other questions, Leo, that you had?
No, I was just wondering, like, let's say that I want to install some like some solar cells in the roof of my house. I guess that it should be possible to do the calculations, right? And or should be simple to do the calculations and simulation to see how much energy I will need to to charge the
Yes.
battery.
Uh, yes. So during the Wolfram Technology Conference, and this presentation is also um, on YouTube. So I can like there is a third party library called Photovoltaics Library that has the cell components, like the solar cell components. And let me bring it up. And I wrote an article about it as well, where we showcase, okay, like for a given, from my location, like we are located in Linköping in Sweden. What is the solar profile uh, that we have here? And based on that, we compute the energy consumption uh, throughout the year. And then in this uh, presentation, I had also like shown how to calculate the power that you can obtain from this solar panel for 50 square meter house. And here uh, you could see the yearly simulation, and then here was the monthly energy output that we get from the solar panels. And from here you could couple it, or you could use this presentation to see if it is favorable, or and in which condition or which months uh, you could use your solar power to power your EV and such.
So one question is, in this case, you use like real data, right?
Yes,
From the solar.
yes, in this case, like for this example, uh, there is something called PV GIS. There's a third part. There is a uh, database. From there, I obtained the solar radiation and ambient temperature data, and then I got the power from my solar like plant. Uh, but yeah, this is side topic than what we are discussing today. But yes, you could model, and if you search for rooftop, if you're interested in this, if you search for rooftop solar with system modeler, you can find it on YouTube as well, in our Wolfram R&D channel. So it's hosted there. Yes.
And just one more, like going back to the thermal management. I guess that it should be possible as well to combine this model or to obtain the data to be used, for example, in finite element simulations,
Yes.
for
S-
example, for the radiator. Or
yes. So what are the applications? Like, okay, one thing is fine. You are trying to design a new drone or new EV, and you want to size the different components, like you have the specification from different suppliers, and based on those specification, you want to see how the final output would be. That is one use case. The other use case, as my colleague Vedat had also shown before, was you can use these models to get boundary conditions. So if you have a FEM model of a battery pack, and then you want to input the the t- the inlet uh, current, or that needs to be fed into your battery pack, or the inlet coolant that needs to be fed to the battery pack, and how the temperature profile across the battery pack s- would uh, would behave spatially. So you need a FEM model, and in that case, you can use the system model to generate those boundary conditions, and you can feed those inputs to your FEM model, and then you could see spatially how the heat is distributed across the 3D space. Uh, right. So yeah. So once you have the model, you can do all those sorts of interesting things. Right.
Right. And another question that I see here is it's regarding the if the files are compatible with the version 14.2, because I guess you have 14.2.1.
Yes. Um, I will have to check because, as I said, like in car body, we have this wake. I've used Modelica components from the Modelica library, but I think in 14.2 or 14.3, Leo, you should correct me. We had some change in the Modelica standard library version. So I have to just double check if we ship with with the version that has all these components that I'm using in my library. I
Pro-
don't know. I have to check.
Probably, I mean, they should work because from point two to point two, point one, it should be like a minimal change. So most of the
Yes.
things should work fine because those are mainly like bug releases.
Right. Then the question is, if I have Mathematica 14.1, does it has the system modeler? I think since version 12, Mathematica comes with system modeler kernel, so you should be able to run the models in the notebook. Um, but as we were discussing with Leo, that some older versions of Mathematica and System Modeler might not have the updated Modelica library in it. So some
Right.
of the components that I'm using might be missing. Uh, but one thing I think should also be possible, Leo, that if you upload the presentation notebook to the Wolfram Cloud, you should be able to evaluate it there. It should work there because it uses the recent version. I'm not sure about the dynamics, but I think it should work there if you want to play around with the manipulates. Right. Um, yes. Okay, Leo. Before one thing I also wanted to highlight was we have this upcoming study group on electric vehicle dynamics. So today what we had was a very brief overview, which was very general, so that everyone can understand and get a feel of it. But we have a study group uh, on this EV modeling part, where we go into more details, where we dig deeper into different subparts like the battery modeling. We devote an entire 1 hour on the battery modeling, and Leo will help me with the power electronics part, uh, like how the switching system, like in the inverters and DC-DC converters work. So we will go into detail into that, and hopefully you will be able to model that as well after you have those sessions. And also we'll look into the different motors, um, like the brushless DC motor and the permanent magnet synchronous machine. and see in detail how those work. And finally, we will have a small thermal management. Uh, like we'll combine a thermal loop with the fluid loop and try to see how you can transfer heat from one location to the other. And if time permits, we will use a heat pump and try to show how a heat pump works in this session. So if you want to dig deeper into different components that we covered today, you please you are uh, more than welcome to join this study group that will have be having in having from June 23rd onwards, right? And if there are any other questions that we have not answered, or if you happen to have those questions, like when you are digesting the content what you saw today, uh, feel free to post your questions on the community thread that Robs has posted the link on the public chat. So yeah, the community post link is on the public chat. So if you have any questions related to this presentation, or if you have any questions related to the upcoming study group, feel free to post it there, and we will be happy to answer. Right. Uh, okay then. So Rob, so with that, it was all from my end.
Okay, wonderful. Thank you very much, Ankit, for a wonderful presentation, and thank you, Leo, for helping with the Q&A. And of course, thank you to our kind audience. That's all we have for you today. But please stick around. We have an after-event survey. In fact, let me share that with you. No, sorry, I don't have it ready. But you will be prompted to it at the in at the when the webinar ends. So please let us know what you think about this webinar, and you can share comments and let us know if you want to if you want us to continue with this type of event. As Sankit mentioned, you can join the community of this webinar of this event. The public in the public chat we have the link. Uh, he also invited you to the upcoming study group. Let me share that link for you again. And lastly, I would like to mention that you will receive the recording of today's webinar along with some other resources that you might find useful. With that being said, it was a pleasure to have you here. Have a wonderful rest of your day. Thank you very much.
Thank you.